This lesson is going to cover the applications of systems of linear equations, specifically systems of two linear equations. We've seen the mechanics of solving systems of equations through graphing, elimination, and substitution. Now we want to put this idea to practice of systems of equations and take a look at two different examples where systems of equations help us solve for two unknown pieces of information. So let's take a look at this first problem and then talk about the process we'd go through to solve it. It says this: Emily and Pranav are selling pies for a school fundraiser. Customers can buy apple pies and blackberry pies. Emily sold 9 apple pies and 13 blackberry pies for a total of $217. Pranav sold 12 apple pies and 9 blackberry pies for a total of $213. The question then is, what is the cost each of 1 apple pie and 1 blackberry pie? So we're given some information about how the quantity of pies sold and the total amount made. And the information that it's asking us to find is cost. Cost of 1 apple pie and cost of 1 blackberry pie. First thing you want to do in an application problem is to write down what you're trying to find. So the first thing I'm trying to find is cost of apple pie. Once you write down what you're trying to find, give it a variable name. Since it's apple pie, I'm going to give it a variable name of A. The other thing that I'm trying to find is the cost of blackberry pie. Cost of blackberry pie. Okay, that's the other piece of information I'm looking for. I'm going to give that a variable name as well. I'm going to give it the variable name B for blackberry. Okay, so that first step is to identify what you're looking for. What are the things that you're supposed to solve for? We did that. Well, we have 2 things that we don't know. That means we need 2 equations to solve for those 2 unknown pieces of information. Now, we need to set some equations up. So in order to understand what type of equation we need to set up, we need what's called a governing equation. A governing equation is an equation that uses the information given and the information looked for in the same equation. Okay? So as we look through this, let's take a look at the information that we have given. For Emily, we have the number of apple pies she sold and the number of blackberry pies she sold for a total of $217 of sales. You'll notice that we have the same exact information for Pranav. For Pranav, we have how many apple pies she sold, how many blackberry pies she sold, and her total revenue, how much she made. So if we look at this, we can hopefully see that a governing equation here might look something like profit from apple pies plus profit from blackberry pies is equal to total profit. We're given information about quantity sold, and then we're given the piece of information about total profit. Well, and the pieces that we are hoping to find, you'll see, will fit into this equation as well. Let's take a look first at Emily and see if we can fit the information given into this governing equation. So Emily sold 6 apple pies. Emily sold 6 apple pies. Okay, well, what is the total profit from the apple pies? Well, it's her 6 apple pies times the cost of each apple pie, A, 6A. So the term 6A represents the total profit she made from apple pies. 6 pies times $A per pie. Well, we can do the same thing with her blackberry pies. She sold 13 blackberry pies at a cost of B dollars per blackberry pie. That's one of our unknowns that we gave a variable name. So 13 times B gives us the total profit she made from her blackberry pies. Well, we know from the information given that this is supposed to equal her total profit, which is $217. $217. So we have an equation set up here that utilizes the information given plus contains the two variables that we are trying to solve for. However, one equation with two unknowns, I need another equation in order to be able to solve. So let's take a look now at Pranav. Okay. We can set up a similar equation for Pranav. Well, she sold 12 apple pies. Well, her total profit from the apple pies is 12 times the cost of each apple pie, which is A. We're going to add this, just like we did with Emily, to her total profit from blueberries. Well, she sold 9 blueberry pies at a profit of B dollars per pie. So 9 times B gives the total amount she made from blackberry pies. And we know from the information given that her total profit is $213. So hopefully you see here that we now have two equations with two unknowns. And they just so happen to be the same unknowns, A and B, cost of an apple pie, cost of a blackberry pie. So at this point, we can write these two equations together as a system of equations. And now we can solve this system of equations to figure out the values of A and B. Well, deciding between elimination and substitution, I see that I can quickly make this 6 right here into a negative 12 by multiplying by negative 2. So what I'm going to do is I'm going to use the process of elimination. So multiplying that top equation by negative 2 produces negative 12a minus 26b is equal to, what is that? That's going to be 434. And my bottom equation of 12a plus 9b is equal to 213 will stay the same. So here is now the rewritten system of equations that I can add together, and the a's will be eliminated. So the a's being eliminated, those cancel out, give me 0. Then I have negative 26b plus 9b. That's a positive, negative, sorry about that. That's a minus 17b is equal to, and I forgot to put the negative right here. The negative 2 times 217 is negative 434. So negative 434 I'm going to do negative 434 plus 213 should give us negative, what is that, 221, I believe. Negative 221. So we have a negative 17b is equal to negative 22.1. Finishing off solving for b, we divide both sides by negative 17. And what do we end up with b? We do negative 221 divided by negative 17. And that produces 13. So b is equal to 13. Well, now that we know what b is, we can go back to one of our equations, plug 13 in for b, to be able to solve for a. So I'm going to pick the Emily equation. Okay, so this Emily equation here, I'm going to do 6a plus 13b is equal to 217. This 13 right here, I'm going to plug in for b. So that's going to give me 6a plus 13 times 13 is equal to 217. So we do 13 times 13 gives us 169. So 6a plus 169 is equal to 217. Finishing solving for a, subtract 169 from both sides. 6a equals 217 minus 169. I believe that's going to give us 48. There it is, 48. Finishing off, divide by 6. A equals 8. So we set up a system of equations based on the information we know, plugging that information into our governing equation, and solved the system of equations that was constructed from that to find out that b is equal to 13 and a is equal to 8. That means that apple pies are $8 a piece and blackberry pies are $13 a piece. And there we have it, the solution to this application of systems of equations. A governing equation allowed us to set them up, and we were able to find the two unknowns with the information given. So there's the first example that we want to take a look at. We do want to take a look at one more example together. It is set up a little bit differently, and it'll take a different governing equation to be able to solve for it. So let's go ahead and take a look at it. Here's what we have. We have this. It says a boat traveled 420 miles downstream, well, then turned around and came back. The trip downstream took 14 hours. The trip back took a lot longer, 42 hours. It says this, what is the speed of the boat in still water, and what is the speed of the current? Okay, so if we have a boat in the water, specifically a river in this case, and you're going downstream, the speed of your boat plus the speed of your current gives you your total speed. And when you're going against the current in a river, well, that current is fighting against you, so your total speed is the speed of your boat minus the speed of the current. That's why it's asking us for these two specific things. What is the speed of the boat? Here's the qualifier, in still water. In other words, if the water's not moving, what would be the speed of the boat? And then it also wants us to find speed of the current. So let's write those two things down that we're supposed to find. Speed of boat. Well, speed of boat, I'm going to give that a b as a variable name. And then speed of current. Speed of current. Well, current, I'm going to give that c as a variable name. So we have b, the speed of the boat, c, the speed of the current that we're supposed to be finding. Well, we need a governing equation in order to fill in the information we're given. Well, we're given information about distance traveled. We're also given information about time, and we're asked to find information about speed. Well, in physics, we have a nice, simple equation that relates to us what speed is. Well, we know speed primarily from driving. We know speed is miles per hour. Well, miles is a distance measurement. Per means divide by. Hours is a time measurement. So our governing equation here is going to be speed is equal to distance over time. This is an equation that most people are familiar with. The speed is distance over time, miles per hour, feet per second. Light years, the distance. Light years would be a distance. Okay. There's several other options of what speed could represent, centimeters per hour, so on and so forth. It's simply a distance over time. So we want to set up this governing equation or two of these governing equations given the information given. So let's first focus on downstream. Okay, so downstream, if we want to set something up for speed equals distance over time, first off, what is our speed if we're going downstream? Well, as I said earlier, downstream, you would have your speed of your boat if you were in still water, plus the speed of the current added together to give you your total speed down the stream. So B plus C would give you speed equals distance. Well, what's the distance traveled? They traveled 420 miles downstream, divided by time. What was the total time it took them to travel that 420 miles downstream? Well, it was the 14 hours. 14 hours from right here. So we've set up an equation of speed equals distance over time for downstream. And we have an equation with the two unknowns that we're trying to find. Now let's look at upstream. Some differences here. Upstream, if you're going upstream, you're fighting against the current, which means that your total speed, as we set up this equation, your speed is going to equal the speed of the boat minus the speed of the current, because the speed of the current is peeling some of that speed away from you because it's fighting against you. So B minus C would be speed is equal to distance. Well, again, they traveled all the way back upstream, that 420 miles, divided by time. Well, because they're fighting against the current, it took them 42 hours to travel that 420 miles back. So we now have two equations built off of this governing equation of speed equals distance over time. And these equations contain the two pieces of information that are unknown. Well, I'm going to simplify these two equations really quick. I'm going to go B plus C is equal to, 420 divided by 14, we'll find out is 30. Then we have over here, B minus C is equal to, 420 divided by 42 is 10. So we've simplified both of these equations, but now I can take these and put them into a system of equations since they share the same variables. So here's my system of equations. B plus C equals 30 and B minus C equals 10. Equals 10. So let's take a look at what we've got here. I've got a system of equations that I now want to solve. Well, I see that this is already perfectly set up for elimination because I have a positive C and a negative C. If I add them together, it will cancel out. So let's add these two equations together. First, we have B plus B. That gives us 2B. Then plus C plus negative C. Well, those cancel out to give us 0 equals 30 plus 10 is 40. So 2B is equal to 40. Dividing by 2 produces B equals 20. B equals 20, we found half of our solution. To find the other half, we take one of our equations. I'll take this top one right here of B plus C is equal to 30. And I'm going to take the B equals 20 and plug it in for the B. So 20 plus C is equal to 30. Solving this for C real quick, we subtract 20 from both sides to get C by itself. That produces C equals 10. So we already solved for B, and now we've also solved for C. What did B represent? B represented speed of boat. Well, the speed of our boat is equal to 20 miles per per hour. And then the c represented speed of current. And the c is equal to 10 miles per hour. So fitting the information given into the governing equations along with the pieces of information we were trying to find, that is the speed of the boat and the speed of the current, we were able to set up a system of equations in which we were able to find the speed of the boat and the speed of the current.